Hello everyone. My name is Samar, and today I will be presenting on the topic Technical Insights into Ethereum Layer 2 Optimism. Our agenda will cover the basics of Ethereum, the need for Layer 2 solutions, and a deep dive into Optimism, a prominent Layer 2 solution. Before we start, I'd like to talk about a vibrant and dynamic community called DoraDojo. DoraDojo is an open-source knowledge community focused on cutting-edge technologies such as encryption and Web3, co-built by hackers. DoraDojo regularly organizes and shares sessions in the form of live broadcasts, audio, and text. The topics covered include L1 and L2 consensus algorithms, architecture, and related content in GitHub repositories. Some of the specific topics covered include Scroll/Polygon zkEVM, Eigen's hybrid proof system, Starkware, Aztec, Optimism, Zcre, Aptos, Move, cryptography, including zero-knowledge proof, public key encryption, hash functions, and lattice ciphers, distributed systems, the Ethereum protocol stack, quantum computing and quantum information, and satellite communication and spacecraft system design. The DoraDojo community is constantly expanding and inviting new members to join. If you are interested in learning more about cutting-edge technologies and staying ahead of the curve, I encourage you to contact Dojo at DoraDojo0 on Telegram and claim your bounty. The dojo welcomes proposals for new content, and they will fund and share it. So, whether you are an experienced developer or just starting out, DoraDojo is the perfect community to learn and grow alongside like-minded individuals. Join us today and let's explore the world of cutting-edge technologies together. Now we will start an overview presenting on the topic Technical Insights into Ethereum Layer 2 Optimism. On the title slide, we have the title of our presentation, Technical Insights into Ethereum Layer 2 Optimism. In the overview, we'll cover the structure of today's presentation. We'll start with a brief introduction to Ethereum and the challenges it faces. Then, we'll discuss the concept of Layer 2 solutions and why they are necessary. Following that, we will dive into Optimism, a prominent Layer 2 solution, and explore its technical architecture. Layer 2 solutions are designed to enhance the scalability of blockchain networks like Ethereum. They aim to reduce gas fees and improve transaction speed without compromising security. Layer 2 operates on top of Layer 1, which is the base layer. We'll compare Layer 2 with Layer 1 to understand the limitations of Ethereum's main network, such as high gas fees and slower transaction times due to its consensus mechanism. Layer 2 addresses these issues by processing transactions off-chain and only recording final results on Layer 1. Optimism is a Layer 2 solution built to scale Ethereum by using optimistic rollups. It allows for faster and cheaper transactions while maintaining the security of Ethereum's Layer 1. We'll look at its technical architecture, which uses rollups to bundle multiple transactions into a single batch, reducing the load on Layer 1 and improving overall efficiency. We'll also include a diagram to illustrate the interaction between Ethereum Layer 1 and Optimism Layer 2. Then we will move to optimistic rollups. Assume transactions are valid by default, hence the name optimistic. This approach reduces the need for immediate computation verification, unlike other rollup solutions. Key components include fraud proofs and challenge periods, where validators can challenge the validity of transactions during a specific period, ensuring security. Sequencers manage the order of transactions, maintaining a streamlined process. We'll include a diagram showing the workflow of optimistic rollups, detailing the steps involved in processing transactions. The canonical transaction chain, CTC, is essential in Optimism's architecture. It batches transactions and submits them to the Ethereum main chain, ensuring data availability and finality. A CTC transaction includes the transaction data and metadata, organized in a specific structure. Understanding this format is crucial for developers working with Optimism. We'll include a flowchart detailing the lifecycle of a CTC transaction from submission to finalization. Optimism supports a wide range of applications, including DeFi projects, NFT platforms, and various dApps. Its ecosystem is rapidly growing, with continuous innovation and integration. We'll discuss some of the key applications and future developments aimed at enhancing scalability and user experience. To summarize, Optimism provides a robust solution for scaling Ethereum, offering significant improvements in transaction speed and cost. Its innovative use of optimistic rollups ensures security while enhancing performance. A written manuscript of this lecture will be provided for further reference. We'll also provide a list of references and further reading materials to deepen your understanding of Optimism and Layer 2 solutions. 1. Introduction to Layer 2 Blockchain. Layer 2 solutions are designed to enhance the scalability of blockchain networks like Ethereum. They aim to reduce gas fees and improve transaction speed without compromising security. Layer 2 operates on top of Layer 1, which is the base layer. 2. Comparison with Layer 1, such as Ethereum's main network, faces limitations like high gas fees and slower transaction times due to its consensus mechanism. Layer 2 addresses these issues by processing transactions off-chain and only recording final results on Layer 1. What is Optimism? Optimism is a Layer 2 solution built to scale Ethereum by using optimistic rollups. It allows for faster and cheaper transactions while maintaining the security of Ethereum's Layer 1. Technical architecture. Optimism uses rollups to bundle multiple transactions into a single batch, which is then recorded on Ethereum's main chain. This reduces the load on Layer 1 and improves overall efficiency. Let's take a look at the diagram illustrating the Optimism architecture and its interaction with Ethereum Layer 1. 1. User transactions. The process starts with user transactions, represented by the first box in our diagram. 2. Optimism Layer 2. These transactions are sent to the Optimism Layer 2, which is designed to handle a large volume of transactions efficiently. 3. Optimistic rollups. Within Layer 2, optimistic rollups are used to bundle multiple transactions into a single batch. This significantly reduces the number of individual transactions that need to be processed by Ethereum's main chain. For Ethereum Layer 1, these bundled transactions are then recorded on Ethereum's Layer 1. This ensures that all transactions benefit from the security and decentralization of the Ethereum main chain. 5. Confirmed transactions. Finally, the Ethereum main chain processes these batches, ensuring security and verification before confirming the transactions. By using this method, Optimism enhances transaction speed and reduces costs while preserving the robust security features of Ethereum. This makes it an excellent solution for scaling the Ethereum network. Here is a sample code for implementing optimistic rollups using a simple smart contract on Ethereum. 1. Batch structure. The batch struct holds information about each batch of transactions, including its ID, the root hash of the transactions, and whether the batch is confirmed. 2. Batches array. The batches array stores all the batches that are submitted. The next batch ID keeps track of the next batch ID to be assigned. 3. Submit batch function. This function allows anyone to submit a new batch of transactions. It creates a new batch, stores it in the batches array, and emits an event. Confirm batch function. This function allows anyone to confirm a batch of transactions. It marks the batch as confirmed. Get batch function. This function allows anyone to retrieve information about a specific batch by its ID. This is a simple example to illustrate the concept of optimistic rollups. In a real-world scenario, there would be additional logic to handle disputes, fraud proofs, and more complex data structures to manage the transactions within each batch. 1. Explanation of optimistic rollups. Optimistic rollups assume transactions are valid by default, hence the name optimistic. This approach reduces the need for immediate computation verification, unlike other rollup solutions. Technical details. Key components include fraud proofs and challenge periods. Validators can challenge the validity of transactions during a specific period, ensuring security. Sequencers manage the order of transactions, maintaining a streamlined process. Let's take a look at the diagram illustrating the workflow of optimistic rollups. 1. User transactions. The process begins with user transactions, represented by the first box in our diagram. 2. Sequencer. These transactions are sent to the sequencer. The sequencer is responsible for managing the order of transactions, ensuring they are processed efficiently. 3. Optimistic rollups. Once ordered, the transactions are bundled into optimistic rollups. At this stage, the transactions are assumed to be valid by default. For Ethereum Layer 1, these bundled transactions are then recorded on Ethereum's Layer 1. This ensures that all transactions benefit from the security and decentralization of the Ethereum main chain. 5. Challenge period. After being recorded on Layer 1, there is a challenge period. During this time, validators can challenge the validity of any transaction. This ensures that any fraudulent transactions can be identified and addressed. 6. Valid transactions. If no challenges are raised during the challenge period, the transactions are confirmed as valid and proceed to the next stage. 7. Fraud proofs. If a transaction is challenged and found to be invalid, fraud proofs are used to verify the challenge. 8. Transaction rejected. Invalid transactions are rejected based on the fraud proofs, ensuring the integrity of the system. By utilizing optimistic rollups, we achieve faster and cheaper transactions while maintaining the robust security of the Ethereum network. The combination of sequencers, challenge periods, and fraud proofs ensures that the system remains secure and efficient. Let's dive into a practical example of how optimistic rollups can be implemented using Solidity, the programming language for Ethereum smart contracts. Here, we have a contract named Optimistic Rollup. This contract is designed to handle the submission and challenge of state roots, which are essential elements in managing rollup transactions. We start by declaring a public variable state root of type bytes32. This variable will hold the current state root of our rollup, representing the latest valid snapshot of transaction data. Next, we define two events, state root submitted and state root challenged. These events are crucial for transparency and auditability, allowing network participants to monitor changes and challenges in the rollup state. The submit state root function allows a sequencer to submit a new state root. When a new state root is submitted, it is stored in the state root variable, and a state root submitted event is emitted, logging the new state root and the address of the sequencer. The challenge state root function provides the mechanism for participants to challenge the validity of the current state root. If the submitted state root does not match the existing one, a state root challenged event is triggered, identifying potential fraud or errors. This simple example encapsulates the core mechanics behind optimistic rollups, showcasing how transactions are processed in an efficient and secure manner by leveraging the power of Ethereum's smart contracts. Through this code, we understand how optimistic assumptions in rollups help in scaling Ethereum. By allowing transactions to proceed without immediate verification, but with the possibility of later challenges ensuring the integrity of the system. The canonical transaction chain, CTC, is essential in Optimism's architecture. It batches transactions and submits them to the Ethereum main chain. This process ensures data availability and finality. A CTC transaction includes the transaction data and metadata, organized in a specific structure. Understanding this format is crucial for developers working with Optimism. Let's examine the lifecycle of a CTC transaction from submission to finalization, as illustrated in the diagram. 1. User submits transaction. The process begins when a user submits a transaction to the Optimism network. This transaction is the initial step in our flow. 2. Once submitted, the canonical transaction chain, CTC, batches the transaction. This batching process groups multiple transactions together, preparing them for efficient processing. 3. In the next step, the CTC adds essential metadata to each batch. This metadata includes information necessary for the identification and verification of transactions, ensuring that each transaction is properly accounted for. 4. After adding the metadata, the CTC submits the batch of transactions to the Ethereum Layer 1. This step is critical as it leverages the security and decentralization of the Ethereum main chain to secure the transactions. 5. The submitted batch is then included in an Ethereum block. This inclusion signifies that the transactions have been recognized by the Ethereum network and are part of its immutable ledger. 6. Once included in a block, the transactions are considered finalized. This finalization means that the transactions have passed through all necessary checks and are now complete. 7. The final step in the process ensures data availability. By recording the transactions on Ethereum's main chain, the CTC guarantees that the transaction data is available and can be referenced or audited in the future. This detailed lifecycle highlights the robust and secure nature of the canonical transaction chain in Optimism's architecture. It showcases how transactions are efficiently batched, securely processed, and ultimately finalized while ensuring data availability. Let's dive into a practical example of how the canonical transaction chain, CTC, can be implemented using Solidity, the programming language for Ethereum smart contracts. Here, we have a contract named Canonical Transaction Chain. This contract is designed to handle the submission, batching, and finalization of transactions, mirroring the lifecycle we saw in the diagram. We start by defining two structures, transaction and batch. The transaction structure holds individual transaction data, including the sender's address, the transaction data, and the timestamp. The batch structure groups these transactions together and includes metadata and a finalized status. We then declare an array batches to store all transaction batches and a variable next batch ID to track the next batch ID. Two events, batch submitted and batch finalized, are defined to log the submission and finalization of batches. These events are essential for transparency and auditability. The submit transaction function allows users to submit transactions. It creates a new transaction and adds it to the current batch. If there are no batches or the last batch is finalized, a new batch is created. The finalize batch function finalizes the current batch, marking it as complete. This function also emits the batch finalized event, logging the finalization. The getBatch function retrieves information about a specific batch, including its ID, metadata, finalization status, and the number of transactions. Finally, the getTransaction function retrieves details of a specific transaction within a batch, including the sender, transaction data, and timestamp. This code example illustrates how the CTC concept can be implemented to batch and process transactions efficiently. It showcases how transactions move from submission to finalization, ensuring data availability and security. Here's another example of Solidity code that demonstrates a more detailed implementation of the canonical. Let's explore another example of how the canonical transaction chain, CTC, can be implemented using Solidity, providing a more detailed approach with metadata handling and a basic challenge mechanism. Here, we have a contract named Canonical Transaction Chain. This contract is designed to handle the submission, batching, finalization, and challenging of transactions, following the CTC lifecycle we discussed. We start by defining two structures, transaction and batch. The transaction structure holds individual transaction data, including the sender's address, the transaction data, and the timestamp. The batch structure groups these transactions together and includes metadata, finalization status, and a challenge flag. We declare an array batches to store all transaction batches and a variable next batch ID to track the next batch ID. Three events are defined: batch submitted, batch finalized, and batch challenged. These events log the submission, finalization, and challenging of batches, respectively, providing transparency and auditability. The submit transaction function allows users to submit transactions. It creates a new transaction and adds it to the current batch. If there are no batches or the last batch is finalized, a new batch is created with initial metadata. The finalize batch function finalizes the current batch, marking it as complete and emitting the batch finalized event. The challenge batch function allows users to challenge a finalized batch. If a batch is challenged, it is flagged, and the batch challenged event is emitted. This mechanism provides a basic way to ensure the integrity of the transactions. The batch structure groups these transactions together and includes metadata, finalization status, and a challenge flag. The getBatch function retrieves information about a specific batch, including its ID, metadata, finalization and challenge status, and the number of transactions. The getTransaction function retrieves details of a specific transaction within a batch, including the sender, transaction data, and timestamp. This enhanced code example illustrates how the CTC concept can be implemented with additional features such as metadata handling and a basic challenge mechanism, ensuring the security and integrity of the transaction processing. Optimism is a Layer 2 solution for Ethereum that significantly enhances scalability and reduces transaction costs while maintaining the security of the Ethereum main chain. Let's explore the diverse and rapidly growing ecosystem of Optimism, as depicted in this diagram. Starting with the applications, Optimism supports a wide range of use cases, primarily categorized into three major areas. 2. NFT platforms. Non-fungible token (NFT) platforms also thrive on Optimism. The reduced fees and faster transaction times make it an ideal environment for minting, buying, and selling NFTs, thereby supporting a vibrant digital art and collectibles market. 3. dApps. A wide variety of decentralized applications, dApps, operate on Optimism, spanning multiple sectors such as gaming, social media, and beyond. These dApps leverage Optimism's scalability to provide smooth and responsive user experiences. Looking ahead, Optimism is committed to continuous innovation and improvement. Key future developments include: 1. Optimism aims to further enhance its scalability. By continuously refining its technology, it seeks to handle even greater volumes of transactions, supporting the growing demand from an expanding user base. 2. Improving user experience is a top priority. This includes making interactions more intuitive and seamless, reducing friction for users, and enhancing the overall accessibility of applications built on Optimism. Optimism fosters an environment of continuous innovation. This involves integrating cutting-edge technologies and developing new features that keep the platform at the forefront of blockchain technology. Finally, ongoing integration efforts are crucial. Optimism is working to ensure that its Layer 2 solution is compatible with a broad array of tools, services, and other blockchain networks, fostering a more interconnected and robust ecosystem. The ecosystem of Optimism is characterized by a dynamic range of applications and a forward-looking approach to development. As it continues to grow and evolve, Optimism remains a leading Layer 2 solution, driving innovation and enhancing the capabilities of the Ethereum network. Here example code 1, Simple Optimism Ecosystem Contract. Solidity code. Let's take a look at a simple contract that represents the ecosystem of applications on Optimism. 1. Introduction to the contract. This contract, named Optimism Ecosystem, allows users to add and retrieve information about applications running on the Optimism network. 2. Application structure. The application struct holds information about each application, including its name, category, and owner. 3. Applications array. The applications array stores all the applications that have been added to the ecosystem. 4. Adding an application. The add application function allows users to add a new application by providing its name and category. The application is then stored in the applications array, and an event is emitted for transparency. The getApplication function allows users to retrieve information about a specific application by its index in the array. This simple contract illustrates how applications can be managed within the Optimism ecosystem, showcasing the ease of adding and retrieving application data. Example code 2, Enhanced Optimism Ecosystem Contract with future developments. Now let's explore a more detailed contract that not only manages applications but also tracks future developments within the Optimism ecosystem. 1. Introduction to the contract. This enhanced contract, named Enhanced Optimism Ecosystem, allows users to add and retrieve information about both applications and future developments. 2. The application struct now includes a timestamp for when the application was created, in addition to its name, category, and owner. 3. The future development struct holds information about upcoming features, including their description, implementation status, and target date. 4. The add application function allows users to add a new application by providing its name and category. The application is then stored in the applications array, and an event is emitted. 5. The add development function allows users to add information about a future development, including its description and target date. This information is stored in the developments array, and an event is emitted. 6. The Get Application function allows users to retrieve information about a specific application, including its creation timestamp. 7. The Get Development function allows users to retrieve details about a specific future development, including its implementation status and target date. This enhanced contract provides a comprehensive view of the Optimism ecosystem, allowing for the management of both current applications and future developments. Optimism is a Layer 2 solution designed to scale Ethereum through the use of optimistic rollups, providing faster and cheaper transactions while maintaining security. The technical architecture involves batching transactions into rollups and submitting them to Ethereum's Layer 1. The canonical transaction chain, CTC, is key, ensuring data availability and finality by batching and recording transactions on Layer 1. Optimistic rollups assume transactions are valid, with fraud proofs and challenge periods adding security. Optimism's ecosystem includes a variety of applications such as DeFi projects, NFT platforms, and dApps. Looking forward, future developments focus on enhanced scalability, improved user experience, continuous innovation, and broader integration, solidifying Optimism's position as a leading Layer 2 solution. I've gathered 10 comprehensive resources that delve into the technical and functional aspects of Optimism, a Layer 2 solution for Ethereum. Cointelegraph and CoinDesk provide overviews of Optimism's architecture and governance models. Cointelegraph, CoinDesk. The official Optimism website and Boardroom offer detailed insights into its ecosystem and community-led governance. Boardroom, Home. Crypto-Rated and LimeChain explain the interaction with DeFi, NFTs, and the scalability improvements. Crypto-Rated, LimeChain. Benzinga and Coinpedia discuss Optimism's historical context and investment potential. Benzinga and Coinpedia FinTech News. Finally, ChainStack provides technical details on bridging and interlayer communication. ChainStack. These resources collectively highlight Optimism's role in enhancing Ethereum's scalability and its promising future developments. Thank you all for your time and attention throughout this presentation on Optimism, a leading Layer 2 solution for Ethereum. We've explored the core concepts of Optimism, including its technical architecture, the canonical transaction chain, CTC, and the role of optimistic rollups in enhancing scalability and reducing costs. We've also delved into the vibrant ecosystem of Optimism, which supports a wide range of applications from DeFi projects to NFT platforms, and the exciting future developments that promise to further enhance its capabilities and user experience. By leveraging the power of optimistic rollups, Optimism ensures faster, cheaper transactions while maintaining the robust security of the Ethereum main chain. Its community-driven governance model and continuous innovation highlight its commitment to building an inclusive and efficient blockchain ecosystem. For further information, I recommend exploring the resources from Cointelegraph, CoinDesk, Optimism.io, and other reputable sources to deepen your understanding of this groundbreaking technology. Once again, thank you for participating, and I look forward to any questions or discussions you may have.